In this video, we're going to be talking about complements and conditional probability. We talked a little bit about complements before, so the notation for a complement was writing that line over it. So if you have some event A, the complement we would denote with a line over it, and it means not an A, or just not A, you could write. So we use this idea a lot, using the complement when we're calculating probabilities. In this first example, Topford Development Limited supplies X data DVDs in lots of 50, and they have a reported defective rate of 0.5%. If a quality control engineer wants to carefully analyze a defective disk, what is the probability of her getting at least one defective disk in a lot of 50? Is the probability high enough that the engineer can be reasonably sure of getting a defective disk that can be used for her analysis? So we have the probability of a defect given to us in the word problem here. And so the probability that we're going to find a defect is 0.5%. We want to write that as a decimal, which means we need to move our decimal point two positions to the left. So 0.5% would be the same as 0.005. So what we're interested in finding is the probability of at least one defect. And at least one means the probability of 1 or 2 or 3 or all the way up to 50, since there are 50 disks in the lot. And so this would be a really big and yucky calculation to do, and the only thing that's not included in this list is 0. And so it would be much easier for us to find the probability of the complement, and so there's the probability of 1 or 2 or 3 or 4 all the way up to 50, and then 0. So that would be everything if we included 0 in there. So the probability of this whole thing would be 1 minus the probability of no defects. So the first thing that we need to do here then is calculate the probability of a disk not being defective. And since the probability of having a defect is 0.005, not having a defect would be 1 minus 0.005. So that's 0.995. So now this probability, 1 minus no defects, and of course this is also going to be raised to the 50th power. So it's going to be 1 minus, the probability of not having a defect, 0.995, and that's in all 50. So that would be raised to the 50th power. So get out your calculators and compute that. So 1 minus 0.995, and then raise that to the 50th power. And you should get 0.22167 or 1687. So we would round that to 0.222. So when you're typing this into your calculator, you would do 1 minus. You don't really need parentheses, just 0.995. And then your calculator should have a symbol that looks like this. So you would want to hit that symbol. And then 50. And then enter. So on your calculator, this is what you should type. And now the second part of this is this probability large enough that the engineer can feel pretty safe that she's going to find a defective disk to analyze? And I would say because this probability is so small, the engineer should use more than one lot. So having a 22% chance that you're going to end up with a defective disk is not very high. So I would say that it would be a good idea to pull another box or another lot of disks. In our next example here, if you make random guesses for 10 multiple choice SAT test questions, each with 5 possible answers, what is the probability of getting at least one correct? If these questions are part of a practice test and an instructor says that you must get at least one correct answer before continuing, is there a good chance you will continue? So again, this is an at least one problem, so we're going to have to use the same concept as above. So first, probability of a correct answer. So 1 out of the 5 is correct. So the probability that you will get it correct is 1/5. And probability at least one correct. Again, this is going to be the probability of 1 or 2 all the way up to 10. And so that's not a easy calculation to do. What's a lot easier is to do 1 minus the probability that none of them are correct. So if we're concerned with not having something correct, then the probability that your answer is not going to be correct is going to be 1 minus 1/5. And that's 5/5 minus 1/5 is 4/5. Whoops. And so then this probability is going to be 1 minus the probability that they're all wrong. So that would be 4/5. Now this time there are 10 questions, so it would be raised to the 10th power. And you could compute what 4/5 is as a decimal. That might be easier for you to enter into your calculators. So 4/5 is the same as 0.8. So 1 minus 0.8 raised to the 10th. And you should get 0.8926. And so we would round that to 0.893. Is that a pretty good chance that you're going to continue? And the answer is yes. You have an 89% chance that you will be continuing. Next we have the formula for conditional probability. It's here, again, this is not a formula that you need to worry about memorizing because most of the time we're going to just be doing this intuitively. So the probability, so this is the probability of B given A, and so this represents the probability that event B is going to occur under the assumption that event A has already occurred. So here is the formula, the probability of A and B happening at the same time divided by the probability of A. And again, you will not need to memorize this formula. Here's the example that we've been using for a lot of our problems, and I've put in some of our conditional probabilities along with some OR probabilities so that we can get some practice doing all of those together. Okay, let's take a look at example A. If one of the 1,000 test subjects is randomly selected, find the probability that the subject has a positive test result given that the subject actually uses drugs. So now we know ahead of time that the subject uses drugs, So when you're looking at the table, you only want to be looking at this line in the table that deals with someone that we know uses drugs. And so we are interested in a positive test result. So that's 44. Out of the total for this line is only 50. So it's 44 divided by 50. And if you compute that, you get 0.880. Example B, if one of the 1,000 test subjects is randomly selected, find the probability that the subject actually uses drugs, given that he or she had a positive test result. So now this time, we're told and we know ahead of time that our test subject has been tested positive. So we only now want to look at these two numbers, 44 and 90, to compute our probability. So we want the probability that the subject actually uses drugs. So subject use drugs is the first number, so that's 44 again. Out of our total this time is 44 plus 90. So that's 44 divided by 134. And computing that on your calculator, you should get 0.328. The next one, if one of the 1,000 test subjects is randomly selected, find the probability that the subject used drugs or had a negative test result. So this time we want used drugs or had a negative test result. So there are used drugs is the 44 and the 6. And then we also want had a negative test result. So that's actually both of these, the 6 and the 860, but we've already added the 860, or the 6 in. So we don't add that in again, we only add to that the 860. So it's going to be 44 plus 6 plus 860 divided now by our total, because we weren't given anything. We don't know any information ahead of time this time. So this is going to be out of our total. And that gives us 910 over 1,000, which is 0.910. In example D, if one of the 1,000 test subjects is randomly selected, find the probability that the subject used drugs and had a negative test result. So now this time it's the word and. Oops, I'm going to switch my colors. So for this one it was or. One or the other, or both. For and, it means that they both have to be happening at the same time. So that's the difference between or and. Or is, for example C, that they used drugs, or they had a negative test result, or both of those. For example D, we want the probability that they used drugs and they had a negative test result. Both of those were happening at the same time. So when we go up and look at our table, we want used drugs and negative test result. So used drugs and a negative test result, that is the 6. So that, and that's the only number in the table that is using drugs and negative at the same time. So that's going to be 6 divided by 1,000, and that gives us 0.006. In the next one, if two of the subjects are randomly selected without replacement, find the probability that the first person selected had a positive test result and the second person had a negative test result. So the first person having a positive test result would be 134, so the 44 and the 90. out of the total number of people, 1,000. For the second person, we want a negative test result. So the negative test results are the second column, and that's 866. But now we've already taken someone out, so the total number of people that we're choosing from is 999. So let's compute this probability. So we could type in parenthesis 134 times 866, close off your parenthesis, and then divided by another parenthesis, 1,000 times 999. And I'll write that out so that you can see it. And we get 0.116. So I typed in 134 times 866. Oops. Divided by 1,000 times 999, and then enter. In the last example, if two of the subjects are randomly selected, this time with replacement, find the probability that the first person selected had a positive test result and the second person had a negative test result. So this is the same as the problem above, it's just that now we're replacing that person. And so for a positive test result, it's still going to be 134 divided by 1,000 for the first person. But now the second person, for a negative test result, it's going to be 866 again still, divided by, now we've put the first person back, so there's still 1,000 people to choose from. So it's not going to change our probability a bunch, but it will change it a little bit. So we're going to do parenthesis 134 times 866, so our numerator doesn't change, and then divided by 1,000 squared. And we get 0.116 again. So again, you'd have to go out a little bit further in your decimal places to see the difference. This one was 0.116044, and the problem above was 0.11616. And there were more decimal places, but that's far enough to see that there is a slight difference in our probabilities. So again, to enter this in your calculator, you would do parenthesis 134 times 866, close your parenthesis, divided by, and this time you could just do 1,000 squared if you'd rather do that. Okay, so that is it for this lecture. Let me know if you have any questions, and have a great day. Thanks.